All right, today we're taking a look at 7-2 solving exponential equations. You guys can scratch inequalities off topics today. We're not going to worry about exponential inequalities. All right? So, again, today we're kind of looking at solving things. Hopefully this is pretty straightforward. We'll look at some applications as well. Some of these problems might even seem familiar. We've actually hinted at some of these strategies in previous chapters as well. Okay. So first off, solving exponential equations. At this point, we don't know how to undo exponents. So when we're solving equations, we undo addition with subtraction. We undo multiplication with division. Okay. At this point, we haven't learned how to undo exponents. Okay. The only process we have kind of in our tool bag at this point is to write everything with the same base. Okay? And this is where it might seem a little familiar to some. Okay? So 4 to the 2n minus 1 equals 64. Well, I know 64 is 4 to the third. Once I have now made both sides with equivalent bases, what do I know? Well, hopefully, we know the powers have to be the same. Then we'll add 1 to both sides. We get 2n equals 4, which means n must be 2. So the goal of these problems is to get our bases to be the same, then we can equate our powers. Looking at this next example, we have 5 to the 5x. I'm going to leave that alone, but there is some way that I can change 125. Well, 125, hopefully you know, is 5 to the third. When we now look at this, remember our properties of exponents. Power to power, we multiply. So we wind up with 3x plus 6 as my power. I have two sides that are equivalent to each other. Both bases are the same, which means the powers must be equivalent as well. If I subtract 3x from both sides, I'm going to get 2x equals 6, which means x equals 3. Again, some of these problems should look very familiar to you. We actually have done some of these back when we were talking and working through properties of exponents with section 6.1. Okay? Get the bases to be the same, equate your powers. All right? When we apply this to a situation, we're looking at solving. Okay? We're measuring bacterial growth in science class. You take an initial look at a measurement where there's 2,500 bacterial cells in a petri dish. After 4 hours, that petri dish is overflowing with 17,000 bacterial cells. Okay? Just imagine that, like a petri dish sitting on the counter and there's just goober like growing over the sides of it. Ugh, disgusting. All right? The question is, how many cells would we expect after 12 hours if this were to continue to grow? All right, little joke there. Got the old 5-second rule with the old potato chip you dropped on the floor. Okay? Remember our model that we've been using has always been this. Okay? We're going to simplify it today because I don't necessarily care what my rate is. If I do care what my rate is, it's going to be pretty easy to figure out based on things. But what I'm going to do is I'm going to transfer this just to a number. All right. Actually, most times we're just going to say that's x, not t, but x is generally time because it could be, years, hours, days, whatever. Okay. So this is our general equation or exponential equation we're going to use. So we take an initial measurement where there's 2,500 cells. So just like yesterday, A is going to be our starting amount, right? After 4 hours, there are 17,000 cells. The question is, do I know my growth rate? No. So this is what I need to solve in this case. We do know how to solve. We're going to divide both sides by 2,500. We want to isolate that power. We're going to get 6.8 equals b to the fourth. You're going to ask yourself, how do I undo a fourth power? Well, I undo it with a fourth root. I'm going to wind up with b is the fourth root of 6.8. Super important today, when you're calculating things, do not round that value until the very end of the problem. Okay? If you round now, you're going to have the incorrect answer in the end. So when we go to estimate after 12 hours how many cells there are, I want to actually put in that decimal value. You can use it stored in your calculator. I don't know what it is off the top of my head, so I'm just going to use the fourth root of 6.8 here. And we're looking now for how many cells there are after 12 hours. Okay. If I wanted to figure out my rate, what I would do is calculate that value, and I would just subtract 1 from it. That would give me my decimal rate, which I could convert to a percent, and that would be how fast my bacteria is growing. Right? At this point, we just want to figure out the number of cells, so I'm going to round to the nearest whole cell. All we have to do is plug that into our calculator, and we wind up with 786,080 cells. That is absolutely disgusting. So are you going to pick that potato chip off the ground now? What do you think about that? I mean, it stays there for 12 hours, probably not, but 5 seconds, maybe you're still okay. All right. So that's an application of our exponential equations. Next thing we're going to go to, we'll talk a little bit about money. All right. Everybody likes making money, so we're going to talk about compound interest. All right. So if you look, this is kind of just our different ways of investing. So principal, what's in B, that is the case where you put your money in a mattress. All right. So a mattress. All right. You put it under your bed. You hope that it turns into something, but it really doesn't. It just stays the same amount for the duration. Simple interest is right here. So simple interest. So simple interest, you only earn interest on your principal value, which is why this one is linear growth, because the amount that you're earning interest on never changes. It's always that initial $1,000 you put in. You earn interest on the 1,000. You don't earn interest on your money that you made after time. All right. Compound interest is here. All right. Compound interest. Whoops. If I can spell. Oh my gosh. Bad day, huh? Compound interest is when you make money on the money you made. Okay. So compound interest continues to make money. So after a year, instead of $1,000, you might have $1,005. Okay. So then the next year you'll earn interest on the 1,005, not just 1,000. Okay. That's the difference between simple and compound. It starts slow. All right. But over time, you can see how as we continue to make money on our money, it's going to grow a lot faster than with simple interest. All right. And that's why investing early can really help you in the long run. So if you were to invest, $20 a month, from your job at Hy-Vee or whatever, if you were able to put $20 away each month, all right, it's not a ton in the long run. So it's $240 a year. But you think about that, if you did that for the rest of your life, all right, it would grow substantially, right? We can kind of run through the models and see how that would work when we check out our formulas, which are down here. These formulas are super important to know. And this is what we use for compound interest, okay? These formulas here, notice, are the same. This is used for a finite number of times. This is compound continuously. I don't know why I write conti, who knows, whatever. All right, compound continuously. The first two, again, are finite number of times. The third example is compounding continuously. All right, so we're going to look at 3 options for investing. You obviously want to make money. Having more money is better. All right, so this is really similar to our A times B to the X. All right, it's just we're calculating interest a certain number of times. Bank A is going to give us 5% compounded daily. So I'm going to start with my initial amount. I'm going to take my rate, which is 5%, and I'm going to compound daily. So what you're going to do is you're going to divide your rate by 365 because you get 5% for the year. So we're going to take 5%, we're going to divide it evenly over those 365 days, and then we're going to raise it to the 365, and we're investing for 10 years. Sorry, I had to look at that. All right. So the reason we do this is we divide our annual interest rate by the number of times we're going to calculate it, which in this case is 365 times a year. All right. Then we raise it to the 365 times 10 because over the course of 10 years, you're going to calculate that interest 3,500 or 650 times. That's why the power is that instead of just a 10. Because if we're calculating interest daily, we're going to need to calculate our interest 3,650 times over a 10-year period. Okay? You can use your calculator to figure this out. Just make sure, if you do use your calculator, either calculate that out and type in 3,650 or put your power in parentheses. You're going to wind up with $8,451.96. Pretty good deal. An extra $3,400 just for letting your money sit. I would take that. All right, the next situation, we have $5,000. Bank B is going to give us 7% compounded annually. All right, so those cheapskates, they're only going to calculate our interest once a year. All right, over a 10-year period. So 10 times 1, they're only going to calculate our interest 10 times. This doesn't sound like a spectacular or stellar deal. All right, but the nice thing with this bank is they do have a higher interest rate. Sorry, one sec as I'm typing this in my calculator to get my answer. We wind up with $9,835.76. All right. So in that situation, much better deal. Even though we calculated interest less, we wound up with more money in the end. Sorry, I'm going back to this last one, and I just typed it in, 365 to 360. This is not the right value. We wind up with $8,243.32. My apologies there. 0.05 divided by 365, 3650. Yep. 5,000, 1.07, the 10. Yep. All right. So even though this is a better deal, we do wind up with more money, even though we calculate interest less times over that 10-year span. We have a higher interest rate. That kind of balances things out. So this bank looks to be a better option at this point. The last option we're going to explore is compounding continuously. Continuously is you are compounding interest an infinite amount of times. You are constantly calculating and earning interest, okay? So that's where this number E comes into play, all right? We'll show you exactly where it comes from later in this chapter, okay? But this number is an irrational number. It's kind of like pi, but we use it a lot with calculating continuous interest, all right? In this case, that's our base. Our power is going to be our rate, which is 375, and then we multiply it by 10. So 0.375 times 10 is our new power. We're calculating that interest continually, and notice this one, even though we're calculating interest an infinite amount of times, we do wind up with the least amount of money, but this example also has the lowest interest rate, okay? So kind of rate and number of times you calculate interest plays into your decisions. So if you had these three investing options, I don't know about you, but I would choose B because I want to make some money for doing nothing. All right? Know those formulas. They will not be given to you on a quiz. So make sure you know the difference between compounding a finite number of times and compounding continuously. Keep in mind, we do have a textbook assignment and a worksheet. Make sure you do both and submit when you're finished. If you do have questions, ask during the Google Meet or utilize the discussion board. Yeah, have a good day.